Now we're ready to write the correct recurrence relation. So recall that Tij is the min cost triangulation of the section Ij, and I've drawn the section Ij here. It's a piece of the polygon, and I've drawn the jump edge back from J to I in blue dotted lines. So recall that every section must have exactly one jump edge, or at most one jump edge. Now we would like to break this section up into smaller pieces, and in particular the optimal triangulation will break it up in some way, and we want to make sure that when we break it up we end up with sections or have at most one jump edge. So the trick is to observe that the jump edge itself has to be part of some triangle when you break it up. So this jump edge Ij is going to be part of some triangle. Let's say it's part of some triangle IJK, and I'm going to suggestively draw the edges IK and KJ in dotted blue lines. Clearly the vertex K can take any value between from I plus 1 all the way up to J minus 1. So our optimal value would be the minimum over all possibilities of K equal to I plus 1 to J minus 1 of, if we use the triangle IJK, then we pay for its perimeter. So we pay perimeter of IJK, and then you will have to subdivide the section I to K, which should cost TIK, and then you have to subdivide the section K to J, which would cost TKJ. So this would be a recurrence relation. Each Tij is a min over up to n possibilities, where you range over all places where the vertex K can be between I and J. So that's the correct recurrence relation. And note that the way we are breaking it up, both the pieces that we produce have at most one jump edge. So therefore, we always take sections and break it up into sections. What is the order in which we'll solve these subproblems? And what is the runtime? I will let you figure these out. Given the recurrence and the definition of subproblem, these are nice exercises to work out. Okay, the reason we are looking at all these different kinds of dynamic programming examples is to sort of get accustomed to the various kinds of subproblems that one could encounter. So let's make a list of all kinds of subproblems that we've seen so far. So firstly, if you have strings, then the kind of natural subproblem that one might think about is prefixes or suffix. So if you have your input to be, think of an input as an array of 1 through n, then you can have prefixes which start at 1 or suffixes which end at n. And if you have pair of strings or triple of strings, then you can think about subproblems which are pairs of prefixes. If you have a pair of strings xy, then the natural subproblem one could think about is prefixes of x and prefixes of y, or if the problem needs it, maybe prefix of x and suffix of y, and so on and so forth. These product constructions are useful if you have 2 different or 3 different objects and you can break up each one into pieces. Then sort of looking at all possible products of these pieces is a very useful thing to do. In this particular example that we saw, we actually looked at neither prefix nor suffix, but a more general thing, which is a section. So you have these items 1 through n, and we looked at some section between I and j. And this is what happened in our example on min cost triangulation. If you have trees in your problem, it's actually very useful to have look at subproblems which are subtrees. So you can take your tree and root it at a node, and once you root the tree at a node, for every node you would have descendants and ancestors. And now if you look at the subproblems which consist of subtrees of your subtrees rooted at the nodes of your tree, that's a very good class of subproblems, and that's the reason why many optimization problems on trees can be solved efficiently using dynamic programming. And if in some cases you do work with exponentially many subproblems sometimes, just because you get a better exponential algorithm. So for example, in the TSP problem, traveling salesman problem, you have subproblems which look at all possible subsets, and you have a much more efficient dynamic programming algorithm than the naive algorithm for the problem. So you'll see many more examples of different kinds of subproblems on the homework and the discussions.